So, good morning. Today we have with us Professor James Lowenberg-DeBoer from Harper Adams University in the UK. Jess is also the president of the International Society of Precision Agriculture, the ISPA, and he's co-editor-in-chief of the journal Precision Agriculture. He has many more degrees, but we agreed we will have three because that's as much as anyone can take. Jess and I also just submitted a joint proposal to hold a workshop for Israel and UK scientists on data in agriculture. So perhaps next year we'll see him in Israel. But for now we have Zoom. So without further ado, Jess, you may share your screen and begin your talk.
Okay. Good morning, or yeah, I guess it's still morning in Israel. Greetings from the United Kingdom, and thank you very much, Harper, for that introduction. Today, I'd like to share with you some information and thoughts about lessons learned from precision agriculture adoption worldwide. We see another wave of technology coming into precision agriculture, and there's some photos on the slide that indicate some of those new things coming in. So there's autonomous equipment, and the photo there is from Hands-Free Farm at Harper, where we've been growing crops autonomously since 2017. There's a variety of handheld sensors and devices that may make precision ag technology accessible for medium and small farmers. And then there's a whole range of machine vision guided technologies for weed and pest management and other things. But the question is, can we learn anything from the adoption patterns of the past that help guide farmers and entrepreneurs as they introduce this new technology and adapt to it? So the objectives of the talk today will be, number one, to set the context of precision agriculture adoption worldwide. Secondly, to look at why has the adoption of some technologies been very rapid and has lagged for others. And then to ask the question, what can Israeli agriculture and the agri-tech sector learn from PA adoption patterns elsewhere? And the photos here on the slide just give you an example of the range of applications of one basic underlying innovation. So the greenness sensors for nitrogen management can be put into handheld devices, which have been used successfully by small-scale farmers in a number of countries, but they can also be incorporated into large machines like the lower photograph, designed for large-scale mechanized farms. But before I start, I think it's important to give a sparse data warning. So no country in the world systematically collects official data on use of precision agriculture. There's only a few governments, US, Australia, UK, and Denmark, that sporadically do surveys of precision agriculture adoption for crop production. And on the livestock side, reliable data on the use of precision livestock technology is very rare. Manufacturers and dealers don't usually reveal their sales data. That's proprietary. So our knowledge of precision ag adoption comes from piecing together data from sporadic surveys that are geographically dispersed and use very, very different methodologies. So I would like to compare this to looking at an impressionistic painting. So if you stand back from the picture, you can get an overall view and an understanding of what the picture is. If you go too close, you see just a lot of dots, and that don't necessarily mean very much. I'd also like to emphasize that it's important to look at adoption by the specific practice or technology, because precision agriculture is a toolbox. It isn't one technology. This question of are farmers adopting precision agriculture is almost meaningless, because it's adopting which technology, which practice. Farmers choose what's useful, and they leave the rest. So one of the places where the data is the best on precision agriculture is in the US, and one of the longest running data series and most consistent is the Crop Life Purdue survey, which I've been involved with in various ways since the mid-1990s, where ag retailers have been asked about their use of precision agriculture repeatedly every year, every 2 years since that time. And the data on PA use by retailers is valid and important in the US, because for many US farmers, at their initial access to precision agriculture is often through buying a service from a dealer. So this chart in particular is the use of GPS guidance. The gray line is GPS light bars, so manual guidance, which was introduced in North America in the late 1990s. And when we first asked the question in 2000, already 24% of the dealers were using the technology. That rose to 79% in 2009, and then it's dropped off since, because it's been replaced by auto steer, where essentially the driving of the equipment is handed over almost completely to the computer, and that was very rapidly adopted. It's been one of the most rapidly adopted technologies in the history of ag technology. It's used everywhere where there's mechanized agriculture. By ag retailers, it was introduced in North America in 2003. By 2015, it was up to over 80% of the dealers, and it's remained there since. If you add dealers who use manual guidance and auto steer, you come up with almost 100% of dealers using some kind of GPS guidance. It's truly become standard practice for that group. The green line is GPS guided sprayer boom control, which has been adopted almost as quickly as guidance. If we look at the farmer side, this is data from the USDA. It's from the Agricultural Resource Management Survey, so-called ARMS survey. And it's incredibly useful data, but it has a very interesting structure. The survey is done by crop, and it's done sporadically. It's not done on any regular interval of 2 or 3 years or something like that. And it asks about the precision ag use on a specific field in a specific year. So it's an incredibly specific way of asking the question. In the chart, I did not link up the dots there with a line, because they're different crops in different years, but they've been asked essentially the same question, and it's not hard to imagine a line going through those dots with adoption of GPS guidance being with a pattern very similar to that of the ag retailers. So in the most recent surveys in 2016 and 17, about 60% of crop area was planted or managed with some kind of GPS guidance. When it comes to variable rate technology, and the chart here is variable rate fertilizer, we get a somewhat different picture that until about 2010, generally farmer use of variable rate technology was under about 10%, which to me indicates that farmers are interested in the idea. They're trying it, weren't quite convinced that it should be become their standard practice. There's been a little bit of trend up over time, and in the US, there's been intense publicity in the farm press. There's been subsidies in some areas, but use overall has remained modest, that it did go up in one corn survey to almost 30%, but generally it's been 20% or under. On the dealer side, have jumped in and offered variable rate services because it's been a profitable service option for them. You can see that the red line there is variable rate fertilizer. That's being offered by almost 90% of the ag dealers. The green line there is BRT seeding prescriptions, and this is the prescriptions. This is not actual seeding. In the US, almost all farmers do their own seeding, but the dealers are working with them to create prescription maps where they maybe vary plant population or variety hybrid within fields. That has grown enormously. The purple line is variable rate pesticide application, which has lagged over time, been somewhere around 20% for the last decade, been mostly spot applications on perennial weeds and so on, where a reliable prescription map could be created at a relatively low cost. Dealers see that as a growth area, and you can see the dotted line there up to 47% in 2023 is a big increase. And we think that that's because they see the introduction of a machine vision guided equipment targeting pesticide application being introduced into their businesses. There are some cases in which variable rate application of fertilizer has become standard practice. One of the best examples is sugar beet production in the Red River Valley of the North, which is in Minnesota and North Dakota, which is the production area of well over half of the sugar beet in the US. In 2016, they did a survey, and about 53% of the sugar beet acreage in the valley was managed with variable rate nitrogen, and a greater area than that was grid soil sampled, but not variable rated. And if you know the valley, you understand it's an incredibly homogeneous area. It's an old lake bed, and there's very little topography, very little difference in visual soil characteristics. So the fact that you have that high a level of variable rate application is actually quite impressive. And the question is why? Well, part of it is the motivation for farmers, which is what is in the table. The first column of numbers is the yield advantage by properly managing nitrogen application in a variety of studies from the University of Minnesota, North Dakota State, and American Crystal Sugar, which is a cooperative. And if nitrogen is managed properly, the beets have a higher sugar content, which processors like, and so they offer a premium for higher sugar content because their sugar extraction is more efficient when the sugar content is higher. And this all together results in an increased net return. And in these studies that range from $48 to $72 per acre, which is significant. And to complement that, The other pieces of the puzzle were in place. So the fertilizer dealers were set up to apply the variable rate. The crop consultants had invested in the soil sampling equipment and the mapping technology to offer services. The University of Minnesota and North Dakota State University had done the research to identify how nitrogen should be managed. So all the pieces were together there. There was a motivation to do it and the ability to do it quite easily. And so farmers do it. The pieces haven't all come together in very many places. One of the other areas in which there's been lots of discussion around the world and in the US has been the use of agricultural data. There's a little bit of insight into that in the Crop Life Survey. It shows that in 2020, about 2/3 of ag retailers managed or archived data and yield data, soil test data, other data for farmers. About 20% of them pool that data within their customer base, 12% pool beyond the customer base, and only about 4% of the retailers don't help their clients at all with data. Most of that data, at least at the ag retailer level, is used in fertilizer and seed choice decisions. So the top 4 bars there in the chart show the P&K, liming, nitrogen decisions, and then overall hybrid variety selection, where somewhere around 60 to 80% of the dealers show either some influence or major influence on the decision making in those areas. In Europe, the adoption of precision agriculture has been a bit slower, in part because agriculture is in many areas quite different from what it is in the Americas or in Australia, in part because of smaller farm size. There's certainly interest in guidance, which is growing very rapidly in areas with large farm size like Eastern Germany, but overall growing. Use of on-the-go sensing for fertilizer application isn't high, but it's probably the highest in the world because of relatively higher nitrogen prices, higher grain prices. Environmental regulations that's tighter than many areas of the world. So some EU countries have limits on the amount of nitrogen that farmers can apply. And so this motivates farmers to identify where will that nitrogen be most effective and most profitable. So that leads to targeted use of nitrogen, and then some government subsidies for end sensor use. There's growing interest in the kinds of technologies that fit European farming, which include controlled traffic, precision livestock, especially robotic milking, and precision horticulture and viticulture. If we look specifically at the United Kingdom, the last random sample survey of the whole country has been done in 2012, so that's a few years ago, but even then GPS guidance was being used by 22% of farmers, variable rate by 16%. On cereals farms, the rates are higher. Even then, GPS was almost half of farmers, variable rate was 30%. If you look at the chart, it breaks down by farm size. Like almost everywhere in the world, precision agriculture is adopted more rapidly on larger farms. In the UK, farm size is defined by number of workers. So small farm is under 2 workers, larger is over 3 workers. And you can see the gray bars are higher for all of the variable rate technologies indicated. So overall, the UK pattern is similar to the rest of the world, but because of the demographics of farms, the UK has more smaller farms with much more livestock and mixed farms, and fewer of those large arable farms, which tend to lead precision agriculture adoption everywhere. Now, it's interesting to note there's some recent, more limited area surveys done in the UK. There was one in Scotland in 2016, which in particular showed that over 50% of wheat producers were using variable rate nitrogen, and that over 50% of farmers plan to adopt variable rate seeding in the next 5 to 10 years. In the West Midlands, where Harper is located, almost 50% of respondents indicated that they were using variable rate. So these are some of the highest variable rate fertilizer use numbers in the world, but there's some question about what they mean, because the way the question is asked in the UK is different than the way it is asked in the US or some other places. So if they ask in the UK a farmer, do they use variable rate fertilizer, they may be saying, well, yes, I have used it. I don't use it, on every field every year, but I have used it. So they say yes. Whereas in the US, in the ARMS survey, they asked specifically about this field in this year, did you use variable rate? So there are some high rates of use of variable rate in the UK. They may mean slightly different, something slightly different than they do in the US data. Similar picture, and here in the chart, you see the blue bars are percentage of farms, and the orange bars are percentage of crop area. In the first set of bars, you see 70% of farms say they're using some part of precision agriculture. 70% of crop area is farm.
We seem to have lost our speaker. Maybe let's give him a minute to log back on.
Ofer is on mute.
Oh, Jess, you're on mute.
Okay, can you hear me now?
Yes.
Okay, great. Sorry about that. The Danish data shows that larger farms are adopting precision agriculture more quickly, which is similar to the rest of the world.
Jess, we lost your screen sharing as well.
Okay. Well, that
happens.
Okay, I might need to start over here. Okay,
Good.
do you got it back?
We've got it back.
Okay, great. So we're in Denmark. We're looking at the data from the Danish statistics, and the orange bars are percentage of crop area, blue bars percentage of farms. The orange bars are taller because the technology is being adopted on larger farms more frequently. The second group of bars over is RTK guidance, which is being adopted in the most recent study in 2020 on 59% of crop area, 24% of farms. One of the other things that I noted was crop sensors over there on the right are adopted only on 5% of crop area and 2% of farms, in spite of one of the most intensive efforts anywhere in the world to encourage this technology. Variable rate technology is only modest. They did ask the question in 2017, and it was only used on 7% of farms. In France, the data is a bit different. It's collected from the industry side, so from the cooperatives and the manufacturers, not from farmers, but it shows that about 4% of French field crop farmers use computer-controlled variable rate. There's substantial use of remote sensing, mostly satellite remote sensing, but some drones. About 10% of field crop area is managed with some kind of remote sensing, and about 1% of viticulture area. There's been some interest in electrical conductivity or resistance sensing, but this has been less than about 1% of French agricultural land. In Eastern Europe, we see use of the technology, but at somewhat lower rates, probably reflecting both availability of capital and skilled workers. In Ukraine, about 20% of crop area is managed using guidance, and section control and variable rate is used on less than 5% of area. In Hungary, in 2016, there was a survey for the members of the Farm Accountancy Data Network. About 7% of them use some sort of precision agriculture, but only about 2% of the fertilizer spreaders on the farms in the network were equipped to do variable rate. If we turn now to Australia, been strong interest in precision agriculture from sugarcane growers, driven by both economics and environmental concerns, because use of fertilizer by sugarcane growers has been linked to degradation of the environment in the Great Barrier Reef. There's been good public sector research in precision agriculture for viticulture, and some adoption there, particularly in selective harvest. Australia led the development of guidance. So the first commercial guidance technology for agriculture was introduced in 1997 in Australia, and they still lead the world in adoption of that technology. The chart there shows some data up to 2012. So the blue line is use of auto steer. Again, but even by that time was over 70%. The purple line there is interesting. That's variable rate or varying fertilizer rates on different soils. And that by 2012 was over 40%, but it's important to note there that that includes variable changing of fertilizer within fields. And this is an old practice. Farmers would know that some part of their field seemed like it needed a little extra boost, so they would drive slower or cover it twice, and that's included in this data. In Argentina, we get a very similar picture, but from very different data. So the Argentinians report their data in terms of number of machines, so number of variable rate spreaders, number of auto steer units, number of light bars. But you can see the rapid rise of all those technologies. In Argentina, yield monitoring has been especially important. They, in fact, led the world in yield monitoring for combinable crops in the 1990s, in part because of the structure of agriculture. You have many large farms managed by farm managers, where almost all the work is done by contractors. So the farm managers actually don't get out in the field very often. And so the yield maps were new information for them. In comparison, in North America, even the manager of a very large farm probably spends a bit of time on a tractor or on a combine and has some direct knowledge of those fields. Other data suggests that variable rate fertilizer is less than 20% of crop area in Argentina. In Brazil, some data, especially there's data from 2013 from a survey of large commercial farmers, which showed that about 45% of those growers were using something in the precision agriculture toolbox. I think it's particularly interesting that 26% of that total, so out of the 45%, 58% of that 45% said they use variable rate fertilizer. 36% said they did soil fertility mapping. But it's important to understand, okay, what does that mean in Brazil? Because in Brazil, the soil testing grid size has tended to be very large because soil testing costs are very high in Brazil. In the 2013 survey, 14% of farmers used grid sizes larger than 9 hectares. Well, 9 hectares is larger than the average field size in many European countries. Almost 50% used grid sizes larger than 4 hectares, and 80% used grid sizes larger than 1 hectare, which is the most common grid size in the US data, so 2.5 acres. So yes, they're doing more intensive management of fertilizer, but at a coarser resolution than would be the case in many other parts of the world where variable rate fertilizer is used. Robots are being used in agriculture. Industry sources indicate that about 25% of cows in Northern Europe will be milked by robots in 2025. In France, which is the only country where we actually have data, about 10% of French dairy farms used milking robots in 2018, but 70% of farms say they will install robots when they change milking facilities. Weeding robots are being used all over Europe, led by France, where last year roughly 150 robots were being used, mainly for mechanized weeding of vegetable and sugar beet crops. For a US perspective, the 2020 Crop Life Purdue survey showed that about 3% of ag dealerships use robots, which is not a big number, but it shows that there is a beginning there. Precision irrigation is another topic of interest. Variable rate irrigation is technically possible for sprinklers and drip systems. Variable rate irrigation is technically very difficult for furrow and flood systems, which is most of the irrigation in the world. But modern center pivot lateral move systems many of them are capable of variable rate, but that capacity, I'm told, is not widely used in the US. From what I hear, the variable rate capacity is mostly used to eliminate irrigation on non-crop areas, so roads, ditches, rocks, and so on. Not so much to vary rates within the crop field, because there's a lot of uncertainty about how best to do that varying and define those management zones. Drip irrigation can, of course, be done by management zone, but that requires installing the drip lines in certain ways that sometimes are technically difficult, and it also requires determining those management zones before the lines are installed. And that's an issue particularly for perennial crops, orchards and vineyards and so on, where those drip lines may be in place for a number of years. In the UK, most irrigation is traveling systems. Its variable rate is technically possible for traveling boom systems, but as far as I know, is not used. And for rain gun systems, it's technically not very possible. One of the questions that arises is often, is precision agriculture being used by small and medium farms? We do have some data from the US, which suggests that yes, it is. Some of my colleagues at ERS looked at the smallest farms in the ARM survey Again, that's by crop. So they looked at the smallest farms by crop, and the smallest farms differ a bit by crop. So the rice farms, the gray bars in the chart, were a little bit bigger than the corn and soybean farms, which are the blue and orange bars, but still quite small. And what we found is that those smallest rice farms and soybean farms are adopting particularly auto steer, but considering other crops as well. And one of the things that's happening is that in the US at least, smaller farms often buy used equipment that was purchased new by larger farms. And so if technology is introduced in the new equipment market, it takes a few years for it to filter into that used equipment market. Now, of course, these are mechanized farms. So it doesn't say anything about adoption of precision agriculture by the manual farms that are common in Africa and some parts of Asia and Latin America. Use by horticultural producers, and again, there's very little data, but there is a little bit from the US. There's this idea that in general, if a crop is more valuable, it's more likely that precision agriculture would be used. And that's true in broad acre crops. It's more common to use precision agriculture for sugar beets, say, than wheat, because sugar beets are more valuable and you can spend more to manage them. But for horticulture, it doesn't seem quite to follow that same pattern. The chart there is from Florida, and it gives precision ag use by vegetable and citrus growers. The orange bar is no, the sort of yellowish bar is they plan to use it, and the bluish bar is they use it now. So a little bit over 20% of both groups use some kind of precision agriculture, mostly GPS guidance. There's some complementary data from the 2020 Crop Life Purdue survey, which suggests that specialty crop retailers are less likely to offer precision ag services than their colleagues who serve mostly broadacre crop farmers. In Africa, there's been some use of precision agriculture on large farms in South Africa and some large estates elsewhere in the continent. But most of African agriculture is smallholder. It's done manually. So the classic PA technology doesn't really solve their problems. The photo there shows the site specificness of African farming, which isn't precision agriculture, but is very site specific. So in the photo, you see a field of groundnut with a patch of sorghum, which is planted on an old termite mound because the farmer felt like the action of the termites bringing up subsoil, mixing it with organic matter was particularly a good place to grow sorghum. You also see in the background corn and sorghum growing around the farmyard where there's a higher level of organic matter from animal manure and human night soil. So we're in the process of doing a rethinking of precision agriculture technology and identifying what uses could solve the problems of African farmers. Some of the ideas there are handheld nutrient sensors, because in many parts of Africa, farmers don't know what fertilizer to buy. Soil tests are very expensive and hard to come by. Their budgets are very tight, and so they don't know what to buy, so they don't buy any. Could a handheld sensor change that? Maybe. There's also some ideas about using cell phones to communicate remote sensing and other weather and pest information. The problem is complicated because in many places there's very little in the way of an ag input supply infrastructure, so there's no PA services in most areas. And the precision ag research to adapt the technology to African conditions is just starting. The first African conference on precision agriculture was held in December last year. So let's think overall, what can we see in these adoption patterns? One of them is the adoption of guidance everywhere in the world where there's mechanized farms. And this adoption is faster than almost any technology in history, and more widespread. So we can think of the comparison to genetically modified crops, which are rapidly adopted in the places where they're allowed, but they're only allowed in a minority of countries. Sprayer boom control, seed row shutoffs, other technologies linked to guidance are being widely adopted. Why? Okay, the investment in GPS guidance and the related technologies is mostly cash flowed by the reduction in overlap and more efficient field operations. And the other benefits, reduce fatigue, flexibility in hiring, so on, are unquantified side benefits. But the farmers can see that benefit very, very quickly. Variable rate technology, in contrast, has lagged, other than in a few niches like the sugar beets in Minnesota and North Dakota. Rarely exceeds 30%, and in most of the world, rarely exceeds 20% of either farms or acreage. Why? Several issues have been identified. High cost of site-specific information. So grid and zone sampling is typically done manually with samples sent off for laboratory testing. There's the cost of developing the individualized prescription maps. And then there's a lack of demonstrated value. So there's been a lot of work in particular on variable rate fertilizer. Some of those studies show profits, some of them don't. And so there's not as much consistency in profitability as farmers would like to see. And then the cost of being wrong in many cases is not great because the fertilizer in the scheme of things is not that big a cost, and because the environmental impacts of over applying are not measured. And it's also important to note that almost in the 20th century, almost all agricultural technology that was widely adopted was the embodied knowledge variety. And in case you haven't come across that distinction before, information-intensive technology uses field level data to make decisions. It typically requires additional skill and data on the part of the farmer. Some examples include integrated pest management, which has been a struggle in terms of adoption almost worldwide. Variable rate fertilizer or seed, pest management, again, is information intensive. In contrast, embodied knowledge technology, the information is purchased in the form of an input. Typically requires minimal additional data and skill. Classic case is hybrid corn. So there's a lot of science in developing hybrid corn, but the farmer doesn't need to understand that science. I've seen lots of illiterate farmers using hybrid seed very effectively. Other examples include most pesticides and GPS guidance is embodied technology. It's very easy to use. There's lots of science in a GPS unit, but the farmers and the farm workers don't need necessarily to understand that. And it's a strong bet that in the 21st century, a lot of the agricultural technology, which is widely adopted, will be of the embodied knowledge type. So what are the potential technologies as we go forward? Well, some thoughts are on-the-go sensors for fertilizer application have great economic potential. That with the high cost of information, the cost of developing prescription maps, restraining the profitability, if we can, with sensors, make the cost of information less, if we can reduce the number of steps between the sensor and the decision-making and application, and take the human beings out of the loop, we might be able to make that process more profitable. Probably this means adding other information about crop response capacity from, say soil depth or soil type, yield maps, other things to fine tune that application. Currently, these sensors are most widely advanced for nitrogen, but they could be developed for phosphate, potassium, lime, micronutrients. Similarly, there's opportunities for use of machine vision and robots to individualize pest management down to the plant and insect level. There are those who argue that it's not that the pesticides we use are wrong, it's that we've not been applying them correctly. We've been applying them in a broadcast mode where they're applied over a whole field instead of targeting the individual weeds and pests that are needed. That might be done with large-scale equipment like the one in the upper right, the John Deere Blue River See and Spray technology, or it may be done with robots like the one in the lower photograph. And the lower, the robot application of pesticides and targeting them may be particularly applicable in Europe or anywhere where there's relatively small, regularly shaped fields. I've been doing a lot of work on opportunities for robotics and at Harper, because of hands-free hectare experience, we actually have some data which helps us estimate the costs and the potential. The figure here is of wheat production cost curves with either conventional mechanization or robotics. The blue cost curve, and this is costs as how they change over farm size. The blue cost curve is for conventional equipment. The numbers there at each point are the size of the tractor in that equipment set. So a very small 38 horsepower tractor for the small farms, and then rising to almost a 300 horsepower tractor for the larger farms in this analysis. The orange line is the robotic farm using data from Hands-Free Farm. But there, instead of using larger and larger equipment as the farm grows larger, we've added units. So the smaller farms use 1 unit, the medium-sized farm 2 units, and the larger farm 3 units. 2 things to note about those cost curves. One of them is that the robotic cost curve is lower, so it's possible to cut 20 to 30 pounds per ton out of wheat production costs in the UK. And we chose to look at wheat because wheat is well studied and it's easy to make international comparisons. But UK farmers may find other crops to grow more profitably than wheat. The other thing, and which may in the end be more important, is that the robotic cost curve tends to flatten out as smaller farm size. So it's almost at the minimum cost at the second node there, I think 159 hectare farm. One of the other issues or the outcomes of this analysis is that robotics could help reduce farm equipment investment substantially by using smaller equipment more intensively. So, adoption path for field robotics. My hypothesis is that for grain and oilseed production in areas where conventional mechanization is well adapted, so where they have large rectangular fields like much of North America, Australia, parts of Latin America, I think we'll see co-robotic automation of large equipment. The autonomous chaser bins introduced by Smart Ag in 2019 are a precursor of this development. And I think co-robotics, because that reduces the security concerns and safety concerns about having autonomous equipment in a field without a human being present to manage them on site. For fields with smaller, more regularly shaped fields, small autonomous equipment is possible in the next 5 years. For field horticulture crops, the economics of automation is there. We need it right now, but there's many, many engineering problems to solve before that technology becomes common. So some of the implications of crop robotics over the next 5, 10, 15 years. We see retrofit kits for conventional equipment already coming on the market in the US, and I expect them in the UK in the next 5 years. That farm equipment with design for autonomous operation, so without a seat or steering wheel, maybe in the next 10 years. Smart autonomous equipment that can make some decisions using AI, maybe in 15 years, and those decisions might include best path to avoid obstacles, seed depth given seed texture and moisture, optimal herbicide given weed species. On the market side, we can expect to see farm equipment markets disrupted by new entrants with autonomous equipment that radically cut machinery investment costs and crop costs. That we'll see a wide difference among the current leaders in farm equipment on their interest in and their ability to adapt to these changes. We'll also see some changes in farmland markets and either ownership and rental, because there will be entrepreneurs who use autonomous equipment to make a living growing specialized crops on small and medium farms that in the recent past have not been economic. Some other farm management implications of technology in the pipeline. We talked about variable rate fertilizer and sensors, individualized plant management. For many farms, in places where it's allowed, the value of drones for spot spraying will probably exceed that of data collection. But in the UK, at least, drone spot spraying is severely limited. Satellite data will become ubiquitous, and as the availability increases and costs decrease, and better use of small and medium-sized data sets will come before the vision of agricultural big data is mature. And we hope if the grant we just submitted is successful, we'll be able to do some workshops looking at the methodology and approaches for using those smaller and medium data sets. So take-home message. Adoption of precision agriculture around the world has been uneven. So some technologies have been adopted as rapidly as any in history. So guidance is one of those. Others have lagged, like variable rate fertilizer, for very specific reasons that are linked to the costs of implementing them and the benefits. Precision agriculture is a toolbox. Farmers take the tools they need and they leave the rest. So the example there is in mechanized countries, many farmers take the guidance tool, but they're very selective about the rest. And I think it's important to note, both in use and in development of technology, that in the 20th century, most widely adopted agricultural technology was embodied knowledge. And it's likely that the same pattern will hold in the 21st century. So to the extent that technology can be embodied and made easy to use with devices and software and AI and other innovations, it will be more likely to be widely adopted. So thank you very much. If you need a citation for most of this information, it's in an article in Agronomy Journal in 2019. The photo there is Harper. I hope some of you get to visit Harper sometime. It's located out in Shropshire on a farm. And I think it's one of the ideal places in the world to have an agricultural university. So thank you very much for your attention.
Thank you very much, Jess. This was very, very interesting. If anyone would like to ask questions, please go ahead and mute yourselves. Yes, Shachar, you go first.
Thank you for your talk. It was really, really interesting. I have a question about, from your experience, how willing are farmers to implement, I mean, things that would decide for them? Because from my experience, you know, even if you come for things that would control everything for them, they say, well, we still want boots on ground and we want to decide by ourselves. I mean, going forward.
And again, I think that the basic principle is if farmers think that it solves their problem and will benefit them, they are generally quite willing to undertake and use that technology. But in many cases, especially in crops, they don't have the level of trust in the technology. And in many cases, the technology isn't quite there. That the reliability of the results. So if we take the variable rate fertilizer and there's been on-the-go sensors for fertilizer, for nitrogen, particularly for many years, but the results have tended to be quite mixed, that they work some places, don't work others, work some years, don't work others. And so there's been a reliability question. But overall, I think farmers are willing to do that, and they have proven themselves willing to do that. So there's some use of these kind of automatic changes in livestock. So in the US, at least, broiler rations are typically adjusted in large units by the weight of the birds. So going to lower protein, higher energy rations with bigger birds, and that's done automatically. But there aren't many technologies that are quite up to it yet. Thank you for that question.
Next question, please.
I have a question. Pesticides are quite expensive, so I was surprised that the adoption of precision agriculture for pesticides is less than nitrogen. That is much cheaper. Well, what's the explanation? Why?
I think the explanation is mostly due to the fact that it's very difficult to come up with the prescription maps for pesticides. And so most of the site-specific application of pesticides is spot spraying on perennial weeds, where the weeds are the same place year after year, where they are, and you can spot them very easily. Annual weeds move, and insects are typically mobile, and they move even more. And so it's been very difficult to come up, and expensive to come up with those maps. If we can use machine vision to do this on a real-time basis, and so some of the see it and spray it technologies that are out there have potential in increasing that variable rate. But I think it's an information cost and difficulty question.
Ofer, may I ask a question?
Yes.
Please, Iggy.
James, great talk, very interesting. I'm wondering if you have a good example of using drip irrigation with VRA. Drip irrigation is very common in Israel due to water scarcity. And we actually don't have much of a boom systems that is smart. In other words, that you can use the VRA using the boom. However, we encounter issues with the drip irrigation to adjust them to MZ when the MZ is being determined using EMI and other technology. So I'm wondering if you have a good example that we can read and follow.
Okay, so there's been some good studies of using drip irrigation on management. zones. There's been at least a couple of articles published in Precision Agriculture from California on this. But the question still remains, and this is true whether it's sprinkler irrigation or drip. How do you determine those management zones? What's the best way to maximize the effectiveness of the water? I think everything tells me that there's still a lot of question about how to do that, and unless there's a very tight limit on water availability, or the water is very high cost, farmers have tended to be not interested in going in that direction. Where there's ample water, they'll tend to over apply rather than trying to target it more commonly.
We had a question from Yael.
Hello, thank you for your lecture. I would like to ask you, why is it not allowed to use drones for pesticides application in some of the countries that you mentioned? I mean, if these countries use aerial applications, why not drones?
Well, you hit exactly on the point. I think that one of the reasons why there's been so much reluctance to use drone application in the United Kingdom is that there's very little history of aerial application. Whereas, say, in the US or in Brazil, aerial application in some crops has been quite common for decades. And so doing it with a smaller unit is in fact seen as a benefit. The usual comment that I hear when I talk about this in the UK is, why would we let flying robots fly around with poisons in them, and they might crash and accidentally contaminate someone or something. So there's a very risk-averse attitude, and it's taken, at Harper, we've been trying to get permission to apply spot spray from drones for several years experimentally, and we haven't even been able to achieve that, much less being able to do it on a commercial basis. So I think it's two issues there. Is one of them is the lack of history of aerial application, and the second one is the very high degree of risk aversion among regulators.
Would anyone like to ask another question? Someone wrote to me on the chat. Sarah, would you like to ask your question? Okay, maybe she's not with us anymore. In that case, thank you very much, Jess. This was a big eye-opener, I'm sure, for many of us. And I will post this talk to our YouTube channel later so that more people could watch it. Thanks again for taking the time.
Well, thank you very much for the invitation. And my email was on one of the slides. So if you think of a question later, please feel free to send me a message. Thank you, and have a great day.
Thank you. Thanks everyone for attending.